Hi, folks. Sorry I can't be with you today. I'm feeling under the weather. Hopefully, I'll be back later this week. The unit that we're going into, Solutions, Acids, and Bases, is a fun unit and it's pretty quick. It starts with a little bit of notes, then we get into some labs down the line here. So, I didn't want to waste time today, and I thought that it would help for you to get some of the notes that we have to start with out of the way. A lot of them have definitions, and some things that you'll need for later on. So there's a little activity that you can work on later. Um, and so if you've got your notes handouts, remember these ones look like a little booklet. They're solutions, acids, and bases notes. Get those ready and out and ready to go here. We're just going to go through the first part of this, which is definitions of what a solution is and the parts of a solution, and then also a little bit about how we measure solutions and the characteristics that we can describe. Eventually, we'll talk about acids and bases and how we define those, and a little bit about the pH scale and how we can measure pH. And then finally, about a class of chemicals called pH indicators, which are a lot of fun to play with. So, to start, a solution itself is defined as a mixture. It's not a compound, and it's actually a mixture. It could be a mixture of compounds, a mixture of elements, a mixture of several different kinds of either atoms or molecules. They're not bonded together, so the parts of a mixture aren't sharing or transferring electrons. They are just in the same place at the same time. And by definition, the part of the mixture is small enough that it's on an atom or molecule kind of size, and it's mixed within the other part of the mixture, and that'll make more sense in a second. But understanding that solutions are one of a type of mixture. Last year you might have learned a little bit about solutions and suspensions and colloids. Those are all examples that fit into this category, but solutions are the smallest size of particles. So the parts of a solution all have the same root in them, in the name. They have the root sol, and you think about it, that's the root in the middle of the word dissolve at the SOL root. The solute is the material that's being broken up and dissolved. It's being broken up into molecular atom-sized pieces and being surrounded by the other material in the solution. So the solute is one part. The solvent is the other part of the mixture. It's the material that's doing the surrounding. It's surrounding the particles of solute and breaking them up and holding them up in the mixture so that the mixture doesn't separate. When you put the solute and the solvent together, the mixture that you create is called the solution. So we say that solute plus solvent equals solution. Now, there are lots of different examples, and we'll kind of go into that next. But this is an important line to get down, that solute plus solvent equals solution. So the solute and solvent, in theory, can be a solid or liquid or gas. So both solute and solvent can be in any state of matter. Many common solutions, though, have this pattern. Excuse me. They have a solid solute and a liquid solvent, and they form a liquid solution. So many of the times when we're talking about chemicals that are found in solution, this is the general recipe that we're going to get. So there's several different examples that follow this pattern. Kool-Aid. Hopefully most of you have experienced Kool-Aid in your youth, I mean, some of you still might be drinking Kool-Aid from time to time in the summer, but Kool-Aid has sugar as the primary solute. It also adds a little bit of coloring and flavoring in the little drink packet, but that sugar is the primary solute. It's the solid material that is being broken up and dissolved. You add that to the liquid solvent, which is water, and the solution itself then is known as Kool-Aid, maybe by brand name, or at least of the drink, for example. Another good example that still follows the same recipe is salt water. When we think about seawater, for example, it has both sodium chlorides and then some other potassium chlorides and things like that that are the salts materials in it. They're ionic compounds, but they're broken up and dissolved by the water themselves. And the mixture of the two then becomes salt water or seawater. The salt in seawater actually comes from a couple of different sources. Some of the salt actually comes downstream. It is washed from rocks and other materials as the water is flowing through rivers and lakes into the ocean itself. Other components of the salt in seawater are coming from deep under the bottom of the ocean, where you have volcanic activity that spews different kinds of compounds out into the seawater. Things like sulfurs and chlorides can come from that volcanic vents on the seafloor. You also have a small amount of material that is constantly redissolving from the limestone and other types of rock materials that are found in the ocean floor as well. So you get this soupy mixture that we call salt water, for example, and it can vary in salinity or saltiness, so to speak. But salt is the solute, the water is the solvent, and then salt water is the solution or the mixture of the two. It is possible, though, to have solutions that are made of different combinations of phases of matter or states of matter. For example, alloys are usually a solid solution, meaning that both the solute and the solvent are in their solid form, but are melted and then mixed together and then resolidified. So, for example, mixing zinc as a solute into a higher amount of copper, which is the solvent, makes up an alloy called brass, which is the solution in a way. Some chemists think of alloys as being classic solutions. Other chemists think that they belong really in their own category. But metal alloys like brass and bronze and pewter are all sometimes considered solutions themselves. You can have a solid liquid solution. Another example, just like the ones we had on the previous page, would be sap from a maple tree, for example. The sugars that are dissolved in the sap are made by the maple tree. The water that is coming up through the roots kind of helps to dissolve those sugars and hold them up into the mixture. And we call that mixture sap when we tap the tree. We eventually boil it to reduce some of the solvent or the water and make it into syrup, which is still a solution, just a thicker solution. You can have a solid and gas mixture that forms a solution in a way. Soot and air, for example, are what make up smoke. The little soot particles can be very, very small and airborne and surrounded by the gases in the air. And it basically makes either a solution, or sometimes people would talk about this being a colloid instead because of the size of the particles. But smoke can sometimes be classified as a solution or colloid. On the bottom there, some of you have worked with in your lab, you worked with rubbing alcohol, which is a liquid solution. One liquid is isopropanol, which is a type of alcohol. You add some water to it, and you can often call it rubbing alcohol. That's how you would buy it in a store. Rubbing alcohol can come as a 70% solution or sometimes a 90-some% solution, and just depends on how much water is actually in it. Even though the isopropanol has a higher percentage than the water is still considered the solvent, because the isopropanol slips in between the water molecules and is held suspended by them. I know it's complicated, but one of the things that can happen when you're mixing solutions like this is you can take two different volumes of liquids, and when you add them together, you won't necessarily get the same total. So, for example, adding 50 milliliters of pure isopropanol and 50 milliliters of water, you would expect to get 100 milliliters of rubbing alcohol, but you don't. The isopropanol molecules can slide in between the water molecules and, in some sense, kind of occupy the space in between the water molecules. So the overall volume when you mix 50 mils and 50 mils is usually in the under 100. It's in the 90s, kind of upper 90s sometimes, but as low as like 95 mils when you mix the two together. It's an interesting phenomenon, and we can play with that a little bit more when I get back. Then you have a lot of solutions that are a liquid and a gas mixture. For example, when we dissolve the carbon dioxide into water, we will get some kind of carbonated water, which is the basis for a lot of soda pop. You also add a lot of sugar and a lot of flavoring and some coloring and other ingredients, but the carbon dioxide is really what makes the carbonated water a form of this solution. The carbon dioxide is the solute, the water is the solvent, and the carbonated water or soda pop is the solution. Finally, air itself is considered a solution. The primary gas that's found in the air is actually nitrogen. And we mix into the nitrogen some oxygen, makes up anywhere from a quarter to a third of the air. Then there's a small percentage of the air that is other gases like carbon dioxide, water vapor, even smaller percentages of things like noble gases or helium and argon and neon and hydrogen. So the gas itself is a mixture with many gases that are dissolved and surrounded by molecules of nitrogen or N2. And air itself then is the solution. Now we'll resume to writing those down here. Okay, so how do we measure solutions? Basically, the one big measurement we take is the volume of the solution. If you're cooking and it's asking you to add a half a cup of oil, you'd measure the half cup, and that's the volume of the material you're adding. When we are cooking in chemistry, when we're adding ingredients to things, many times solutions are described by how much of it you're going to use. So a solution, remember the term for volume or the definition of volume is the space that the solution takes up. We're often measuring that in metric units of milliliters or liters. And remember, a milliliter is a very small amount, about the size of a cubic centimeter, and a liter is a little bit bigger. Think half of a 2-liter bottle of pop. But it isn't just enough to describe the volume of that solution. You also have to take into account something called the concentration. Think about the concentration as being how crowded the solute is in the amount of solution that you have. So the formal definition is the amount of solute in a certain volume of solution. That's the concentration. So we might measure concentration of solutions that we buy, things like rubbing alcohol or hydrogen peroxide, by using a percent concentration. That tells you, for example, that 3% hydrogen peroxide in a bottle that you buy at the drugstore is 3% H2O2 and 97% water. Chemists also use another measure of concentration called molarity. Molarity takes into account that different solutes have different size molecules and different weights of molecules. The abbreviation for molarity is a capital M. So you've seen before maybe me take a bottle of acid, and the acid that we've used in labs so far this year has been 0.1 molar acid. 0.1 molar is a relatively diluted form of that hydrochloric acid, versus when we were doing some experiments, I used up to 3 or even 6 molar acid. The highest molarity you can get with hydrochloric acid is actually 12 molar, and that's considered concentrated molarity of that molarity. It's as concentrated as it can possibly get, as much solute in that volume of solution as you can crowd in. So different solutes have different abilities to crowd into a solvent, and it's very much dependent on the actual solute on the solvent itself, and also somewhat on temperature. So there's a measurement about solutions called solubility. It's kind of the ability to dissolve more into a solvent. So we define solubility as how much solute can be dissolved in a solvent, and it often depends on that temperature again. For most solid solutes like sugar or salt, warming the solution can lead you to be able to dissolve more material into it. So you can dissolve more sugar into warm water than you can into cold water. For gases, it's actually the opposite. The warmer the solution, the less gas can stay dissolved. So when we think about a warm stream or river, it can't hold as much dissolved oxygen, and therefore fish can't necessarily do as well in that water. Especially trout are very dependent on oxygen level and temperature. This is why we serve a lot of carbonated beverages cold as well. When you serve them warmer, some of the gas tends to fizz out of it before you actually drink it, instead of when it hits the warmth of your mouth and your tongue and it pops and fizzes there. So the solubility of solids and different kinds of gas solutes is something that we can measure and take into account. Everything has a certain maximum solubility for a certain temperature, and that's a quantity that you can look up in different kinds of chemistry dictionaries, let's say. There's a couple more terms that we should talk a little bit about. One is unsaturated. So if you have an unsaturated solution, it means that there's extra solvent that's not being used to hold solute. So we think about if I take a cup of water and I add just a pinch of salt. There's some salt in the water, and we've made salt water, but it's unsaturated. I could still add some more salt to it and get it to dissolve. So unsaturated solutions have a small amount of solute compared to their solvent, and there's still room for more solute to be added at that temperature. So let's say you keep adding solute and it keeps dissolving. Eventually you reach a kind of maximum point. That maximum point is a saturated solution. At that point, if you add more solute, if you add more salt to the water, it's going to just sink to the bottom. It's not going to dissolve. Okay? Some of you might have experienced this with adding sugar to your cereal. I hope you're not doing this, but okay, I'll confess, I've been known to. You might want to sprinkle a little sugar on some cereal, and if you add too much, have you ever noticed it sink to the bottom of the bowl and it doesn't dissolve in the milk? That's because you've reached the saturated point of that milk and sugar mixture. You have no more room for more sugar to dissolve, at least at that temperature, and all of the undissolved solute will sink to the bottom. The solution over the top is considered saturated. Think full. It has no more room for solute at that temperature, and any extra solute will stay undissolved at the bottom of the mixture. There is a condition that's kind of interesting called supersaturation. It kind of happens when solutes are sometimes holding more than you would normally hold at that temperature. Supersaturated solutions are an interesting kind of physics state. You heat up a solution, you add a whole bunch of solute to it, and then you really slowly cool it. And if you don't disturb the solution, sometimes the solute can stay dissolved for a short period of time, but then if you disturb it by even sometimes just bumping it, or sometimes adding just one more little crystal of the solute, it'll all come crashing out and form undissolved solute at the bottom of the container. If you've ever seen the reusable heat packs that you can buy sometimes in the store that they contain something called sodium acetate. And you can boil them. They're a plastic kind of pouch. And once you boil them, all of the solid sodium acetate will dissolve inside the pouch and they'll stay as a liquid. They have a little tiny metal disc inside that when you click it, it will disturb that supersaturated solution and a whole bunch of sodium acetate will come crashing out of the solution. And as it does that, it gives off heat. So it's a reusable hot pack. If I can bring some later this week, I'll show you. All right. But it's supersaturated solutions can happen when you're making maple syrup. If you accidentally kind of boil it down too far, you might be able to can your maple syrup and you've got it all in the jars or in the bottles. And then as it's sitting on the shelf, it looks all fine for a month or so. And then all of a sudden, large sugar crystals can start forming on the bottom of the jar. That's because the original solution was actually supersaturated. And just over time, it got disturbed and some of the extra solute came crashing out. So unsaturated, saturated, and supersaturated are interesting states that a solution can be in. So hopefully we'll get back in person and we can start talking about acids and bases. But I'd like you to make sure that you go through the activity today. I have a crossword puzzle that'll help you sort out some of those terms. If you have any questions, I can probably answer some emails. So if you would like to email me about a question in person, absolutely feel free to do so. I should be back in a day or two. Thanks a lot. Have a good day.